Hi, everybody. Welcome back to Dave's Math Channel. This is another episode of my daily math problems, feature I started maybe about a month ago on this channel. I'm posting, not really daily, but 2 or 3 times a week, I'm posting math problems on the Facebook group Classical Mathematics. I ask people to solve them there. And usually there are a few people who can do this, and there were a couple people who did this one. So anyway, today I'm going to talk about how we can find integral points on two given ellipses. Let's begin. So here's the problem statement. This is actually two daily math problems, very similar ones. I think I posted one like 3 days ago, the other one the next day. So anyway, the first problem I posted was to find all integral points on the ellipse in the xy plane given by the equation x squared plus 5 where y squared equals 105. That's a ellipse in standard form, it turns out, with major and minor axes aligned with the x and y axes, respectively. But the second one is not in standard form. This is a ellipse. It's still an ellipse, but it's a more complicated equation. 2x squared plus 2xy plus 3y squared equals 63. This ellipse is tilted, it turns out. The xy term means that the major and minor axes of the ellipse are not aligned with the x and y axes, they're rotated. And we'll see that when we solve this problem. But anyway, in both of these cases, I'm asking for the integral points on each of these ellipses. So anyway, and this is closely related to another problem I posted. I think my previous problem I posted on this channel was to show that whenever the x squared plus 5y squared is prime, it's always either 5 or congruent to plus or minus congruent to 1 or 9 modulo 20. And for 2x squared plus 2xy plus 3y squared, if that's prime, it's either equal to 2 or it's congruent to 3 or 7 modulo 20. And in this case, 105 and 63 are not prime, but the prime divisors, I think, are the right form. But anyway, that's kind of irrelevant to this problem, it turns out. But anyway, they are the same ellipses I considered in the previous problem. Just thought I'd mention that. But anyway, let's work on the first ellipse, which I'm calling E1. So I'm defining E1 to be the ellipse x squared plus 5y squared equals 105. It's just a set, or if you like, the locus of all ordered pairs x comma y in the xy plane satisfying this equation. But we're only interested in the integer solutions. So, and the first thing you should notice, since this is an ellipse's standard form, if x and y were both positive or non-negative, say that means that they're both in the first quadrant, then due to symmetry, I think it's pretty easy to see that if you replace x by minus x or y by minus y, you still get a solution. So you're actually going to get four solutions in one. You're going to get x comma y minus x comma y minus x comma minus y and x comma minus y. This should be x comma minus y, the last one. So you get a solution in each quadrant. Um, and so we could just write plus or minus for x and y. And so when we're trying to solve this, really we only have to consider the positive solutions or the non-negative solutions. And I think it's easier to start with y because y is more limited. So we know that 5y squared has to be at most 105 because x squared is positive, not negative. So that means y squared can't be any bigger than 21. Well, 21 is not a square. The largest square that's less than or equal to 21 is 16, and that corresponds to y equals 4. So we know that y has to be an integer from 0 to 4 if it's in the first quadrant. And you can just try this by trial and error, and I think you'll find that if you do that, the only solutions you get where x and y are both positive are 10 comma 1 and 5 comma 4. You don't get any solutions for y equals 0, 2, or 3, but you do when y is 1 or when y is 4. So the solutions, and remember you can do plus or minus. So this really gives you 8 points. These are the solutions. The integer points on the ellipse E1 are plus or minus 10, comma plus or minus 1, and plus or minus 5, comma plus or minus 4, where the plus and minuses are independent of each other for each of these ordered pairs. So that's 8 points. And if you want to know what they look like, here's the picture. I showed this on the first slide. And you can see it has this nice symmetry to it. There's just 2 points in each quadrant. In the first quadrant, the one on the upper right, you get 10 comma 1 and 5 comma 4, and then you just get all the reflections. So those are the 8 points on this ellipse. So I think that one was pretty straightforward. That one's not so hard. The second problem is trickier because mainly because this is an ellipse that's not in standard form. So again, the ellipse we're doing here is 2x squared plus 2xy plus 3y squared equals 63. Now we want to find all integer points x comma y on this more complicated ellipse. Well, there's a trick you can use here. You can complete the square. So here's the trick. First, let's double the equation. We're just doubling both sides and move the constant term to the left side. So if you like, we start with 63 equals 2x squared plus 2xy plus 3y squared, and then we could just double both sides. You still get equality if you do that. So you get 126 equals 4x squared plus 4xy plus 6y squared. But now you can complete the square. Note that 4x squared plus 4y squared plus 4xy plus y squared is a perfect square. That's 2x plus y quantity squared. And then you're left with 5y squared. So you get 2x plus y quantity squared plus 5y squared. And now we can rename 2x plus y. We can just call that w. I'm introducing a new variable here. So now we have w squared plus 5y squared equals 126. Well, I think you noticed something interesting about this equation. It has the exact same form as our previous one, except the constant's different. Here we had x squared plus 5y squared equals 105, and here we have w squared, that's just another variable, plus 5y squared equals 126, which is a different constant. But now, remember that w and y both have to be integers, but not only that, w is 2x plus y, and since x and y are both integers, that 2x is always even, and I think I might have made a mistake. No, I didn't. Did I? I'm not sure. I might have made a mistake. I think, oh yeah, they both have to be odd, not for the reason I said, actually, because 126 is congruent to 2 modulo 4. And the only way the sum of two squares can be congruent to 2 modulo 4 is if both of the numbers that are being squared are odd. I actually made a mistake here, but it is true that w and y both have to be odd, but not for the reason I said. But anyway, so now we have to look for the first thing we have to do, and then when we're done, we can substitute back for x. If we solve for x in terms of w and y, we just got x equals w minus y over 2. So now we're going to do the same thing we did last time. We're going to, first range over y because that's easier. And once it, y squared, it can be at most 126 over 5. Well, that's not an integer, but the largest perfect square that's less than or equal to that is 25, which means y could be at the most 5. And we only care about the absolute value of y when we're considering this equation. But we know that y can be positive or negative, and it is worthwhile this time, since we don't have symmetry like we did last time, to consider the sign of y. So y can be plus or minus 1, plus or minus 3, or plus or minus 5. And coincidentally, it turns out that each of those values of y gives you a value of w. When y is plus or minus 1, we get w equals plus or minus 11. When y is plus or minus 3, we get w is plus or minus 9. And when y is plus or minus 5, we get w is plus or minus 1. But now we're not done because we still need x. So once we've solved for w, we still have to solve for x. And I do all this in this table. And I'm not going to go through the whole table here, but you can go through it yourself. Maybe I'll just go through the first few columns of the table. So our first solution is y equals 1, which yields w equals 11. And then x is w minus y over 2. That turns out to be 5. 11 minus 1 over 2 is 10 over 2 or 5. So we get the point 5 comma 1. And now we can negate that point. We can negate any of these points. We can always negate x and y because we do have twofold symmetry of this ellipse. So if x comma y is a solution, then minus x comma minus y is also a solution. That means we really only have to look for 6 points. It turns out there's 12 points on this ellipse. As well tell you that. And then now we can just find the other ones the same way. And like I said, once we fix y, we actually have to look at two different values of w. We have to look at y equals 1 and w equals minus 11. And that's going to give us x equals minus 6. I think I made a mistake here. I'm not sure. One of our points is minus 6. Oh, no, I didn't. So y is minus 6 when w is minus 11 and y is 1. So we get the point minus 6 comma 1, and then we get negative 6 comma minus 1. And I'm not going to go through all these other examples here. You can do that yourself. But I think you can check for yourself that these are the 12 points we get on this ellipse, which I'm calling E2. And then on the right, I show a graph of those points. So anyway, that's the solution to this problem. Um, and there are kind of tricks you can use. This problem is actually even more closely related to the previous one, where I'm looking at primes of the form x squared plus 5y squared or 2x squared plus 2xy plus 3y squared. Because it turns out you can build up all the solutions for primes, and you can look at the prime factorization of the 105 in the first case or 63 in the second case to get the solution. That's another way you can do this problem, but that's more complicated. You have to kind of know some algebraic number theory to do it that way. And the numbers are small enough in this case that you can just sort of do a systematic search. And I didn't even have to use Mathematica to do this except for drawing graphs. So anyway, that completes my solution to this problem. Thank you for watching. Long live math, and I'll see you guys next time. Bye.